Hello, and welcome to this digital 80-minute math Pascal High School trigonometric function lesson. My name is Mr. Schnitzius. I'm one of the 80-minute math teachers at Pascal. We, your 80-minute math teachers, miss you guys. We hope that we get to be in the same room, getting that Pascal 80-minute math magic working once again face to face, but for right now we are computer screen to computer screen, and we appreciate the hard work that you guys are doing, and most importantly we hope that your families are safe and healthy. We hope that you're safe and healthy. If there's anything at all that you or your family needs, please reach out to us and we will get you in touch with all of the resources that Pascal has to offer. So this lesson is to help you with your first graded assignment over sinusoidal graphs. We're basically going to be going over three things right now. Those three objectives are going to be to understand the graphs of sinusoidal functions, understanding where those graphs come from and how they relate to the unit circle that you were learning about before spring break. We're also going to talk about how to do transformations of those sinusoidal functions and their graphs. And then lastly, we're going to apply sinusoidal functions to solving real world problems like you're going to be doing in the 8 problems on your assignment for this week. There's going to be 3 different sections. I'm going to let you know at the end of each one. We're about to transition to a new section. If you want to pause the video at those points and jot down any questions that you have for when you're in your Zoom classes with your teacher. If you're with Ms. Cusis or Mr. Witskill, or with me later, we'll be having Zoom sessions so that you can ask us questions, and it might be helpful to organize your thoughts. Highly recommending that you take notes as we go along, pause the video and think and reflect. We're going to be using the calculator to graph some trigonometric functions. So if you have a calculator, go ahead and get that handy. And if you need one on the Chromebook, you don't have a handheld one, your teacher can show you how to download a TI-84. They do not have a TI-CAS or TI Inspire CX like we use in class for the Chromebook, so we're just going to make the best with what we have. So let's start off doing a quick review from way back when, a whole month ago, when you did your unit circle project. Okay, so here's the unit circle. I know that your unit circle projects were great because the ones that my students made were great. So the 2 trigonometric functions that we're going to focus on graphing to start off with are the sine function and the cosine function. And basically, it all goes off of taking our angle measures that we use as our input values, our x values, and the output values, the y values that we're going to graph are going to be the values of sine. So remember ASTC, this tells us where we have positive values for a certain quadrant. In quadrant 1, both of our values are positive, both cosine and sine. In quadrant 2, only sine is positive, so cosine is negative, sine is positive. In quadrant 3, only tangent of the angle is positive because you have a negative cosine and a negative sine value. And then C in quadrant 4 is for cosine is positive and sine is negative. My pre-cal teacher, when I took pre-cal, taught this as all students take calculus. That's an easy way to remember which quadrant has which function with a positive value. So what I want you to notice when we look at the sine function, that's the one that we're going to look at first. Okay, where does sine begin? If you begin at an angle of 0 degrees, you're looking at the positive x-axis. Well, when the angle measure is 0, either in radians or degrees, the sine value is 0. That's your starting point for that function. And then what happens as you rotate in a counterclockwise manner around the unit circle? Well, your sine values are increasing. From sine of pi over 6 is 1/2 to sine of pi over 4 is square root of 2 over 2 to sine of pi over 3 is the square root of 3 over 2. And then you get to pi over 2 and you have a sine value of 1. And you think, boy, this sine function is great. It is an increasing function. It's just going to keep increasing forever and ever. Well, not so fast, because as you get into quadrant 2, your sine values start falling. Your angle is increasing. You go over to 2 pi over 3, but now your sine value is back to square root of 3 over 2. Then 3 pi over 4 has a sine value of square root of 2 over 2. Then 5 pi over 6 has a sine value of 1/2. And then by the time you get to the sine of pi, you've made it all the way back to 0. Quadrant 3 is going to be the same exact thing, except now we're venturing into negative territory, negative 1/2, negative root 2 over 2, negative root 3 over 2. These are the same values that you had in quadrant 2. They're just reflected across the x-axis, so they get that negative value. You've reached the lowest possible point, and just when you've reached the depths of despair, because you think, oh my goodness, the sine value is really, really negative right now. Don't fear, because it's coming back to get closer to 0, negative root 3 over 2, negative root 2 over 2, negative 1/2, and then it's back to sine of 2 pi, a full 360 degrees rotation, and we're back to a sine value of 0. So in a table, it looks like this. You're going to take, to get the graph of f of x equals sine of x, your x values are going to be all the different values of angles that you could have from the unit circle, and your y values, your f of x values, are going to be the value of sine for that angle. So all we've done is taken those values that we just saw from the unit circle and put them into a table. Start at 0, 0, go to pi over 2, 1. When we're at pi radians, we're back to 0. When we're at 3 pi over 2, we're at negative 1. When we're at 2 pi radians, we're back to 0. Okay, so let's take a look at what that looks like in the calculator. Here is a TI-84 calculator, slightly less advanced than the ones that we use in class. If you don't have a calculator to use at the house, let your math teacher know and they can show you how to download this onto your Chromebook. If you have a CAS, then you should know how, at the house, you should know how to input graphs. And if you have questions about how to do anything on that, then we can talk about that on the online tutoring session. Okay, here we go. So on here on the TI-84, instead of having a trig button, sine, cosine, and tangent are already laid out there for you. So we're going to do sine of x. If you want to put in your variable, you go up to alpha, hang a right, there's x right there. Okay, so that's in y equals. Now we're going to hit graph, and it's really teeny tiny. So let's go back and change our window. Let's hit zoom. We're going to do zoom standard, number 6. And there it goes. Fantastic. That's a little different than the window I was expecting, but we can see a couple different periods, and that's exciting. So if you want to check specific values, you can hit trace. But before we do that, let's just think back to what we said our table had for us. Okay, when the angle is 0, the sine value is 0. Okay, that's what it's showing me right there. Let's see, the highest possible y value I can get is 1. I got really, really excited because I thought that sine was going to keep increasing forever, but then it didn't. It fell back to 0 when the angle was pi. Then it reached the lowest depths that it possibly could at -1, and right when we were really worried for sine and weren't totally sure that they were going to be able to pull it back out, they came right around for us and they went back up to a y value of 0. So let's double check these. So we're going to do trace. So yes, when x is 0, y is 0. That's great. On the trace function, if you just type in the x value that you want to find the y value for and hit enter, the calculator will show you what that y value is. So we want to find pi over, let's do pi over 6, okay? Let's see, unit circle, that was a month ago. Oh, I have to remember that. Okay, let's see. Sine of pi over 6, that's the first stop on the unit circle. I haven't gone very far yet, so is that 1/2 or square root of 3 over 2? I think that's 1/2. Let's see. So pi is the second function above the exponent caret. Pi over 6 we said we were going to do first. Is it 1/2? Is it 1/2? Is it 1/2? Hey, 0.5. There we go. So this 0.523, this is pi divided by 6 as a decimal. Let's try pi over 3. Let's see, that was the square root of 3 over 2. As a decimal, that's 0.866. Bam, there we go. All right, but the ones that we're really interested in are pi over 2. That's supposed to be 1. Yes. Pi, that's supposed to be back to 0 on the unit circle. Okay, that looks pretty familiar. 3.1415926, blah, 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 blah. 3 pi over 2. 3 pi divided by 2, -1, and 2 pi, back to 0. Okay, so what do you notice about this? We started out at 0, 0. We went up to 1, we went down to 0, we went down to -1, we came back up to 1. So if you notice, every part of the graph kind of looks like that. 0, 1, 0, -1, 0. If I had started back here, it would be 0, 1, 0, -1, 0. We could look at that in the table. Let's extend that table out a little bit. So this is those values that we said were the maximum and the minimum. And another thing that we had discussed before spring break was coterminal angles, right? Those are two angles where you land in the same spot on the unit circle, but here, if I've gone 1/4 turn, what if I want to go a 1/4 turn and then another full turn? Well, that's plus 2 pi to land at 5 pi over 2, so that gives me another maximum. What if I'm at 3 pi over 2 and I want to get a coterminal angle after turning another 2 pi radians counterclockwise? Well, 3 pi over 2 plus 2 pi is 7 pi over 2. So every time I travel 2 pi radians, I end up in the same place. So what that means is the length of that distance that it takes to go through one complete cycle, that's called a period. From 0 to 2 pi, that's one period. Then from 2 pi to 4 pi, that's another period. So a period is basically how long does it take to go through a complete cycle? Starting point, maximum, back to the starting point, minimum, back to where you started. That's the basics of the graph of f of x equals sine of x. And lest we get too one-sided and favor sine too much, what if we think about cosine? So you may have noticed this whenever you were making your unit circle project. The values for sine and cosine are very closely related. At pi over 6, you've got √3/2 for cosine and 1/2 for sine. Well, if you go up to pi over 3, they're the same values, just flip-flopped, right? And so there's a lot of similarities between sine and cosine. One thing that I want you to notice is the starting value. So the starting value for cosine, when the angle is 0 degrees, cosine of 0 degrees is actually 1. So this point is actually the inverse of pi over 2. When you have 0 degrees, cosine is 1, sine is 0. When you're at pi over 2 degrees, cosine is 0, sine is 1. And so that's going to be important to notice later on when we're trying to shift these functions and transform them horizontally along the x-axis. But that's an important thing to notice about the cosine function. It has a different starting point than the sine function. So let's look at what that looks like in a table. Here's a graph of, or here's a table for the trigonometric function g of x equals cosine of x. So starting point 0, 1. Here are some different unit circle values. Cosine of pi over 6 is √3/2. Cosine of pi over 4 is √2/2. Cosine of pi over 3 is 1/2. So similarly to the sine function, we're rotating through these values, √3/2, √2/2, and 1/2. Differently than the sine function. Remember, sine started at 0, 0, and then went up. Cosine of x is going to start at 0, 1, and then fall down. So we've got our maximum value here. Then we reach a middle value. The minimum for cosine of x isn't going to happen until we get to pi. Then we're going to go up to 0 again when the angle is 3 pi over 2. And we've completed one full cycle. We're back where we started once the angle is 2 pi and the y value is 1. So let's take a look at what that looks like in the calculator. So we're going to go back to y equals. We've already got our nice sine of x function there. Now we're going to do cosine of x. Hit graph. So in red, there's our cosine of x. Test out a couple of values with trace. Now I want to trace for y2. So if I hit up, it'll take me to the next function. So tracing y2 equals cosine of x. Hey, we already see that it starts at 0, 1. The cosine of 0 degrees is 1. What's the cosine of pi over 2 degrees? That is 0. Then you're pointing straight up, right? You're on the y-axis, pointing up. Okay, what is the cosine of pi? You're pointing to the left, so the cosine would be -1. What is the cosine of 3 pi over 2? Let's see, that's on the y-axis pointing downward, but if I'm on the y-axis, the x value is 0, the cosine value should be 0. Hey, the cosine value is 0. What about if I go back to where I started? What's the cosine of 2 pi? So, what's the cosine of 2 pi? That's 1. I'm back where I start. Okay? So this is the first thing that we want to understand. We want to understand what sinusoidal functions represent, and we want to understand where they come from. Here's a picture of the cosine of x table. As you can see, how long does it take to go from where we start to in the middle to the minimum, back to where we start, to the middle, back to where we started, maximum, middle point, minimum, middle point, maximum. That one period is still 2 pi radians. Okay, from 2 pi, what's the cosine of 2 pi? 1, maximum, middle point, minimum, middle point, back to where I started at the maximum. That's another 2 pi radians. That tells me the length of one period. So just looking at the graph, we can see that there's some important features of sinusoidal functions, either the red one that we're graphing cosine of x or the blue one that we're graphing y equals sine of x. We call these functions, since they repeat over and over again, these are called periodic functions. It's like you're copying and pasting in a Word document, right? Here's one period. I could just, if I copy that, I could hit paste over and over and over again, and it would reproduce the whole graph. Same thing with cosine. I start right here, I go through one cycle, and then I go through that cycle over and over and over again. So since the periods repeat, we call these periodic functions. For each period, let's change our window from 0 to 2 pi and see what that looks like. All right, here's one period of sine. Every period has a middle value. We're going to call that the line of symmetry later on whenever we are graphing these by hand. So I've got a line of symmetry that kind of sets the baseline. In the case of sine, that's where I start. So I'm on the line of symmetry, I go up to a maximum value, I'm back to the line of symmetry, I'm down at a minimum value, I'm back to where I started. If you look at cosine, which is still in red, there is a line of symmetry going through the x-axis, right? But you're not starting at the line of symmetry. For cosine, you're actually starting at the maximum, then you go to where the line of symmetry is, then you go to the minimum, then you go back to the line of symmetry, then you end where you started, you end at the maximum. You can also notice that an interesting question we might want to ask ourselves is, how far above the line of symmetry is that highest point? How far below the line of symmetry is that lowest point? There's going to be a name for that distance from the line of symmetry up to the max point and from the line of symmetry down to the midpoint a little bit later on. So those are just some graphing sinusoidal functions basics. Those are some tips on how to graph and how to understand the graph of sine of x and the graph of cosine of x. We're about to shift gears, so if you have any questions over what we've just talked about, now would be a good time to stop and jot down some notes. Okay, so we're going to shift gears a little bit now, and we're going to talk about how to do transformations of these sinusoidal functions. So the sinusoidal function that we started with is f of x equals sine of x. And what's nice about math is everything's always building on itself, right? Once you're done with something in math, it's not like you can say, oh yeah, great, I learned that, now I'm done with it. No, it keeps on coming back, right? It sure does keep on coming back. So we've done transformations over and over again in this class. Hopefully you're comfortable with transformations. If not, we're going to go over a quick review of what some of these parameters do. So if I've got a parent function for a sine graph, f of x equals sine of x, there are 4 different parameters that can transform that sine function in different ways. I can do I can multiply the whole function by a coefficient. Then inside the argument of sine, I can multiply by some kind of scalar. I can also, inside another set of parentheses, either subtract a value from x, from the angle, or I can add a value to x, which would be like subtracting a negative value for c. And then the last thing that I can do is I can add some number to the end of the whole graph. So hopefully you remember what each of these does. Instead of just saying, let's write down what these do, I want to look at the calculator and see if we can remember from doing what each of these helps us with. Okay, so let's talk about getting these 2 graphs to match up with each other. As you can see, the red cosine function and the blue sine function, they're basically the same. They're just starting in different locations, right? How could I get these to go perfectly on top of each other? Well, if you notice, the maximum point for cosine happens at 0, right? The maximum value for sine happens at pi over 2. So if we could just shift this cosine function over to here, then they theoretically would be perfectly lined up with each other, right? How do I do that? Which value, which of those parameters that we just talked about, A, B, C, or D, does a horizontal shift? Well, that actually happens when you take the angle and you change it. So we're going to do cosine of x minus pi over 2 . All right, let's see what happens. There's our original function. Would you look at that? They're exactly the same. So what that's showing us is when you have a number inside the house, inside the parentheses, that you subtract from your angle, that's going to give you a horizontal translation. Let's jot that down real quick in our notes here. Okay, this value of C shows you your horizontal translation. If you subtract a positive value, that's going to shift to the right. If you subtract a negative value, in other words, if this says x plus pi over 2, then that would shift us to the left instead of to the right. So now let's look at these other parameters. It's a little more nuanced what each of these does, and it's going to be important whenever we're using this to model real-world problems later on. So let's go back, and we're just going to do this based on the sine graph. So I want to be able to compare these to the parent function. So I'm going to clear this one out. Let's look at sine. Oh, that's not what I wanted to do, sorry. sine of x, and let's add 2. You're doing this at the house or in your living room or on the back patio or wherever you are. If you wanted to think through what each of these does, pause the video, try it on your own, see if your prediction works, and then turn it back on. That would be a good idea. All right, so there's our original 1 period of sine. So what happened? That actually kind of looks like a pretty cool drawing. We just moved up 2, right? And more specifically, we changed where the line of symmetry is, right? If we put in a third function, just y equals 2, that value that we added to the parent function shows us where the new line of symmetry is. So when we think about what D represents, that's more than just doing a vertical translation, okay, which it is. But what we're going to say down here is it tells us something important about the line of symmetry. The line of symmetry has the equation, because it's always going to be a horizontal line, has the equation y equals d. All right, so we've got 2 more to knock out. That would be thinking about b, this number inside the argument, but outside the parentheses that tells you what kind of horizontal translation you're doing. So we're going to think about that next. Back to the graph. Get rid of you. Get rid of you. Okay. So let's do sine, and let's put a number larger than 1 inside the argument, and let's hit graph. Let's see what happens. Interesting. So it's got the same line of symmetry, right? The same maximum value, same minimum value. It's just getting there faster, right? Originally, for the blue graph, our period was 2 pi. Let's see what these values are. So right there is telling me that I get back to where I started at 3.1415927. Hey, that looks pretty familiar. That's pi. We're close to it, right? So what that means is our period got smaller, right? How long it takes to get through one cycle got smaller. We got to the minimum faster. We got back to where we started in half the time as we did in the parent function. Then we hit the minimum faster. So we got through one period in exactly half the time that it took for the parent function. Well, why is that? Because we put a 2 right here. So when you put in a larger value in front of your x, a value larger than 1, that gives you what's called a horizontal compression. You're pushing the graph closer together. And let's see, you can probably guess what's going to happen if we do something that's less than 1. Let's say we do sine of x divided by 2 divided by 20. Oops. Sine of x divided by 2. There we go. Here's our original period of 2 pi. So it's the same maximum, right? We're still going up to 1, except it's taking longer. It's taking exactly twice the time that you can see there, right? Before we got to our maximum after we went pi over 2 radians. Now, if we trace, hey, it's double the time, right? It's not just pi over 2 to get up to 1, it's a full pi. It's twice as long. So if half the period is 2 pi, then that means that the full period would be 4 pi, right? We doubled the length of the period. So to kind of put that into something that we can think about what B is telling us. B is telling us how long a period is. The length of one period equals 2 pi divided by that number that we put inside the sine argument, but outside the parentheses where it tells us the horizontal translation. All right, so we've got our, so I guess this would be a horizontal stretch or compression. So the last one that we need to talk about is, hey, what happens if you multiply by constants? So we're going to do 2 times the sine of x graph All right, so let's see. It looks like the period is exactly the same. What happened? We're just multiplying each y value by 2, right? Our parent function maximum was 1. Hey, we doubled that. Now it's a 2. Our parent function minimum was -1. We doubled that. Now it's at -2. So there's a special name for this distance from the line of symmetry. Remember that line of symmetry for the parent function is on the x-axis. The distance from that line of symmetry up to the maximum value is called the amplitude. That's also the distance from the line of symmetry down to the minimum. So let's record that last thing that we need to knock out here. A, just like it was before, is giving us a vertical stretch. If A is above 1, right? Or a vertical compression if A is less than 1, greater than 0. So the amplitude is going to tell us, we can think of that in 2 different ways. It's the distance from the line of symmetry to the maximum y value. And similarly, the distance from the line of symmetry to the minimum y value. The most important word there being distance. When you think of distance, you think about how far it is from point A to point B. When you think of distance, you think of a ruler. What kind of numbers are not on the ruler? Negative numbers. So even if you have a negative value for A, your amplitude is still going to be a positive number. That's why we want to say the amplitude is the absolute value of that number A that you have right there. Okay, one last thing that we're going to look at before we dive into the notes problems that you have is, what if we looked at what that negative value for A would do? -2 times the sine of x Negative, not minus. Forgive me. Insert negative. There we go. Teachers are humans too, right? Growth mindset. Okay. There's the parent function. There's a coefficient of +2. Okay, so there's f of x equals -2 times the sine of x. So it's just a reflection, right? We're just reflecting the red graph, y equals 2 times the sine of x across the x-axis. So you'll notice it's the same exact amplitude, right? From the line of symmetry up to the maximum of 2. That's the distance of 2. From the line of symmetry down to the minimum of -2, that distance is also 2, right? You're just changing the direction that you're going. So that's all that you need to know about how to transform sinusoidal functions. The next thing that we're going to do is look at those 3 example problems that were titled, should have gotten a PDF entitled Sinusoidal Notes. We're going to go through those 3 problems, make sure that you understand how to do those. That'll be a good springboard into your assignment for this week. If you have any questions over any of these transformations, I'm going to put that back up on the screen. If you have any questions about these transformations and how they work, now would be a good time to pause, jot down those questions that you want to ask in Zoom class, and pick it back up once you got those jotted down. Okay, so 3 questions that we're going to solve. And I've got to tell you, one of these problems involves a popular movie reference, so you have to watch the whole video to get the movie reference. Okay, no just skipping right to the end and writing down the answers. All right, a signal buoy in the Chesapeake Bay bobs up and down in the water. During a small squall, it reaches a maximum height of 9 feet and a minimum height of 1 foot. It reaches a maximum at 9:02 a.m. and a minimum at 9:08 a.m. So I've already put 2 of these points on here. I've labeled the axis as feet. I guess I should really say that this is what we're measuring in feet is the height of the buoy. All right, there we go. That's our dependent value. Our independent value is going to be the number of minutes after 9 a.m. So let's see. At 9:02 a.m., it's reaching a maximum height of 9 feet. And at 9:08, it's got a minimum height of 2 feet. I'm sorry about the document camera, y'all. I'm going to try to move that around as little as possible. So what this is telling me, it's telling me that the line of symmetry is going to be exactly halfway between these 2 points, right? This is the maximum point, this is the minimum point. Line of symmetry is going to have to be exactly between those. Okay, what's exactly between 1 feet and 9 feet? Well, that's 5 feet. So I'm going to dash that line of symmetry right there. And if you remember what we talked about with the transformations of sinusoidal functions, that's going to be our value for d. So d equals 5 feet. Okay, what did we notice about how long it took to go through one period? Well, when you're going through one period, if you go from a maximum to a minimum, you're going to reach the line of symmetry exactly halfway in between, right? So what time would be halfway in between 9:02 and 9:08? That would be 9:05. So we're going to have a point right here. And then you got to be careful. You got to really resist the urge to connect those with a straight line. You're like, slope, all right, down 4/3. No, because it's asking you to write sinusoidal equations, right? So that means we need to have a nice smooth curve coming down like this, and then going from the line of symmetry down to the minimum value. It's going to be something a little bit like that. From here, we can use the symmetry of sinusoidal graphs to complete one period, okay? So I know that I'm, to complete half a period is 6 minutes. So I should be back to where I started after 6 more minutes. That's going to be at 9:14. What time is halfway between 9:08 and 9:14? 9:11. All right, and so we're going to go up like so. And we're going to go up and over like so. There's one period. You want both sides of that once you get from your minimum back up to your maximum to be symmetrical. We're going to be grading this more on the accuracy of your points in your equations than the precision of your drawing. Okay, so those are the points that we're now going to try to write some equations for. Well, you might notice that I've only got one of the parameters that we talked about when we were talking about transforming sinusoidal functions. We said that we wanted to know what A was. A is the amplitude, right? How far is it from the line of symmetry to the maximum point? How far is it from the line of symmetry to the minimum point? So that amplitude, it looks like from 5 up to 9, or from 5 down to 1, that amplitude is 4 feet. So I'm going to put A equals 4 feet. All right, and then let's also think about how long one period is. Let's see, from 9:02, I started up, I went down to the minimum, I went back up to the maximum. So one period takes 12 minutes. So that's telling me that B equals 2 pi over 12. All right, now in order to write out our 4 equations, we're going to label this with 4 different points. So 1, 2, 3, and 4. We're going to think about where we are in this cycle for each of these 4 points, and then we're going to write a sinusoidal equation based off of that. Okay, so the first one that we could do would be starting at point 1. If we start at the top of the wave, so that's looking a lot like which type of function? Does that look like more like a cosine function or more like a sine function? Well, cosine was the one that started above the line of symmetry, right? So we would want to use a cosine function to model that. But since the amplitude is 4, we want to do 4 times the cosine. All right, then we want our value of b to go next. In order to get in order to get the period to come out to be 12 minutes, 2 pi divided by 2 pi over 12 would give us 12 minutes. So then our b would be 2 pi over 12. And then we just need to put our starting point in the right place. That's the point 2 for x and 9 for y. So we want to do x minus 2. We need to shift that function 2 units to the right. And then we need to shift our whole function up 5 more units to get to this line of symmetry. So we're going to put plus 5 on the end. So that would be the sinusoidal equation that you would end up with if you started out thinking about this point here, point 1. Okay. Once you have the first one written, the rest of them are actually fairly simple. The rest of them are not any kind of problem. So now we're going to think about point 2. A lot of this is just going to flow through very, very similarly to what we have here, just with some minor adjustments. So let's say that you started on the line of symmetry and you go down. So now we're thinking more like using a sine function. Why? Because the sine function starts right on the line of symmetry, right? Okay, then you ask yourself, is this looking more like a graph of y equals sine of x or y equals negative sine of x? Well, instead of going up to start off with, I'm going down. It's a reflection across the x-axis. So we would want to do y equals negative sine. All right, it doesn't, and I also need to think about what the amplitude is. So this isn't just negative sine, this is negative 4 times sine. The good news is the period is exactly the same, so the value for b is still going to be 2 pi over 12. But if this is the starting point that we're thinking about, now we need to shift horizontally 5 units to the right, because this point happens at 9:05. So it's going to be x minus 5. And the good news is the line of symmetry is still in the same place, so the line of symmetry is still going to be here at 5. All right, third point that we could think about. Sorry, I don't have a pencil sharpener, so I'm trying to pick the sharpest pencil so that you can see this the best. What if we start at the minimum at point 3? So if we start at the minimum and we go up, well, this looks more like a cosine function, right? Why is that? Because we're not starting on the line of symmetry. We're starting off the line of symmetry. Then you think, wait a minute. Cosine of x, that's supposed to start above the line of symmetry, like we did up here at point 1. So we're going to use a negative cosine function. That's why our equation is going to be y equals same amplitude. So I'm going to use negative 4, and I'm going to use a cosine function. Same period. When does this point occur? It happens at 9:08. So we need to shift 8 units to the right. Line of symmetry is still the same. It's still plus 5. Lastly, we can start at the fourth point that we have right here. That would be starting on the line of symmetry and going up. So let's see, does this look more like cosine or sine? It looks more like sine. I'm starting on the line of symmetry. Is it positive sine or negative sine? Okay, I'm starting at this point. I'm going upwards. That's what sine of x does. So this is going to be y equals 4 times sine of 2 pi over 12 times x minus 11 plus 5. So what's neat about this is all 4 of these functions are the exact same. Any one of these that you put in, you would get the exact same thing. It's asking us to find the times between 9 and 9:30 at which the buoy is 6 feet above sea level. So another way of saying that is, at what time does this point occur, and at what time does this point occur? Well, an easy way to do that would be either to just kind of estimate where that's going to be based on the graph. Okay, I didn't draw this with the utmost precision, so what we're going to do is go to the calculator. Put in our function. And the nice thing about this is if you did this correctly, all 4 functions should give you the exact same thing. I'll leave that for you to check. So let's see, I'm going to put in the first one that we did. 4 times the cosine of 2 pi over 12 times x minus 2 and then plus 5. Let's take a peek at the graph. So that's a real problem, right? Because we can't see hardly anything there. So you can do a couple of things here. You can zoom out. There we go. That's a little bit better. So just kind of looking, it looks like I'm expecting to have one, a little before 5 minutes. So we want to find where this graph intersects the graph y equals 6. So first thing you want to think about is the reasonability of your answers, right? These 2 points mathematically make sense, but that's not in a reasonable domain. I guess the way we were defining it would be time before 9 a.m. So if you labeled the x-axis not as time, but as number of minutes after 9 a.m., if you get into negative time, that means you're time traveling, you're going backwards. That doesn't make sense. So the reasonable domain for this problem is anything above 0. So we're more interested in this point right here. So you want to trace yourself to where you're pretty close to that point. If you go to second trace, you can intersect. If you just hit enter, and it'll tell you that that intersection happens at x equals 4.517. Okay, so what exactly does that mean? 4.517. Well, let's see, that would be 4, so x equals 4.517. That would be 904. See if we can find that next one. So trace. Now we want to get to where we're closer over to here. Second trace. Second trace, there we go, intersect. And it'll tell you that the next time it happens is at 11.48. So let's see, that would be at 9:11. The other one would happen. Okay, but you want to find all the times between 9 and 9:30 when the buoy is 6 feet above sea level. So if you want to change your window on here, we want to go to all the way to 9:30. So now we're just going to graph additional periods, right? So we found these two. I'll leave it to you to find the third one and the fourth one and the fifth one. All right. So we're coming up on an hour on this video, I think. We're going to start on the next one, number 2. That's the Ferris wheel problem. All 3 of these problems are posted on Google Classroom. Your teacher may have sent it to you another way. So work through the problems. See if you have questions to ask in the online class. So let's start number 2. A Ferris wheel, 50 feet in diameter, makes 1 revolution every 40 seconds. Center of the wheel is 30 feet above the ground. So here comes your pop culture reference that I promised you. My wife and I recently watched this movie. Oh, I need to be able to go to the... My face was hiding the bar. Okay. Recently watched this movie. It's The Notebook, starring Ryan Gosling. I don't know if this movie came out in 2004, so I don't know if this is still a movie that teenagers watch today. It's kind of a sappy romantic story. Ryan Gosling, teen heartthrob, asks out his future wife by hanging from a Ferris wheel, and he won't let go until she agrees to go out with him. Not a good way to ask somebody out on a date. Kind of seems a little desperate, although the movie doesn't do a great job of driving that point home. Okay, the Ferris wheel is stopped in the movie while he's hanging there. But let's just say for the sake of argument that Ryan Gosling starts right here at the bottom of the Ferris wheel. He goes part of the way up to this point, then another part of the way up to the highest point, the maximum height of the Ferris wheel, then over to here, he's on his way back down, and then he finally reaches the bottom again. Well, what they tell us is that it takes 1 revolution every 40 seconds. So that tells you the length of the period. The center of the wheel is 30 feet above the ground, and the Ferris wheel is 50 feet in diameter. So if Ryan Gosling is starting here at the lowest point, and how have we labeled our axes here? The dependent axis is height above the ground measured in feet, and the horizontal axis, the independent axis, is labeled as the number of seconds after the Ferris wheel begins moving. So at the very beginning, he would be 5 feet off the ground, right? The radius of the Ferris wheel is 25 feet. So periodic motion, how long does it take for him to go 1 cycle? If it's 40 seconds to take 1 full revolution, then to go a quarter of the way would be a fourth of that. That would be 10 seconds, right? So after 10 seconds, he's up to the center of the wheel. After 20 seconds, he's reached the maximum height. That's 50 feet higher than he started, right? Then after another 10 seconds, so that's 30 seconds total. He's back to the center of the wheel, and then rounding it out, he gets back to safety, where he and Rachel McAdams can go on their first date and fall in love and live happily ever after. So again, avoid the temptation to be like, oh great, he's always traveling at a constant rate. Not so. It's a sinusoidal equation that's going to model his height. So it's going to build up like this and then come down. We want to make it more symmetrical than that. There we go. And finally, it's going to tail out like that. So use the last example to help you write out the equation, find the period, find the amplitude. That will definitely help you find the line of symmetry. Solutions are posted on Google Classroom. And if you have questions, bring those to the online Zoom class. And be sure that you make good progress on your assignment. Thank you guys for your hard work. Thanks for listening. Hope that you're safe and that you're healthy. Let us know how we can help you. Even though we're at our houses and not with you face to face, we're still for you guys. We still want to do everything that we can to help you be successful. Thank you guys. Have a great rest of your day. Bye-bye.